Hello, everybody. Welcome back. In this video, we'll be looking at special power functions in complex numbers. So let's look at what a power function is. So power function in the complex numbers. So it looks like this: f of z equals to a to the n times z raised to the n power plus a to the a sub n minus 1 times z raised to the n minus 1 plus dot 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 all the way down to a1 times z plus a0. So it's a polynomial in terms of the complex numbers, right? Where a sub n minus 1, a sub n minus 2, all the way down to a1 and a0 are complex numbers, right? They are complex numbers. And the single power function just looks like this. It's just a singleton power, right? Z raised to the n power, right? Those are different types of power functions. And you have a sum of coefficients along with different powers on Z. Okay. Or you can have a singleton, right? Singleton power function. All right. So let's look at one popular type of power function. F of z equals z squared, right? Let's look at this type. Now we know by de Moivre's formula, right? Oops, jeez. De Moivre's formula, z squared, well, it equals to r times e to the I theta in terms of polar coordinates squared. Well, that equals to r squared times e to the I times 2 theta, right? So we square the radius and we double the angle, right? Square the radius and you double the angle, okay? So let's see what this function looks like if we're given a particular set in the complex plane. So in my z plane, what if I have the upper half circle whose radius is 3, okay? And the argument of z is in between 0 and pi, okay? No, actually, let me make it better. Let me actually make it like this. It's a quarter circle, let's say. But the radius is the same, but the argument or theta, right? Theta is ranging from 0 to pi over 2, let's say, right? 0 to pi over 2. Now, in this function, z squared, all we have to do is we square the radius and we double the angle, right? So that will constitute squaring the radius of that quarter circle and then multiplying the angles in our argument, right? Multiplying theta. So that means we have to multiply the range in the argument of z. So what our set will look like under this function, f of z equals z squared. It will look like the following. So this is the W plane. The U and V is here. So what we're going to do is, okay, so we know that the radius is 3 and the argument is in between 0 and pi over 2 in the z plane. So under F, what that means is the modulus of W is 9, okay? And the argument of the complex number W is in between 0 and pi. right? So I should say less than or equal to, but so in the W plane, this will constitute the upper half circle, right? Where W is 9. So this is S prime and S is over here. So this is what the image would look like, right? It's just a bigger upper half circle, right? So hopefully that made sense. Let's look at another example. Another example will be something like this. Let me position myself here. Find. Uh-oh, that's not good. Find the image for the. Actually, let me do another one. Let's do under the line. Under the line, y is equal to -1/4, right? So this time, in the z plane, we have a line y equals -1/4. Right, y equals -1/4. So this is our set S. And what we want to do is what this set will look like under the function f of z is z squared, right? Now this one's a little bit different because all we're dealing with are points such that the y coordinate is fixed, right? The x is varied, okay? So what that means is we want to look at the real and imaginary components of the complex number of complex function f of z equals z squared, right? So if z is equal to x plus iy, then the function, right, this will equal to x plus iy squared. And this will equal to x squared minus y squared plus I times 2xy. Okay, so this is our function f in this case. So the real component, u, is x squared minus y squared. And v is equal to 2xy, right? So this is the function in terms of its real and imaginary components. So this is another way to figure out what the image of a set would look like. Just write out z is equal to x plus iy and factor out into its real and imaginary components. Okay. So since we know that y is equal to -1/4, so what these sets of equations will look like if y is equal to -1/4, this would mean that u is equal to x squared minus 1/16, 1/4, -1/4 squared. And then v is equal to 2 times x times -1/4, right? So therefore, u is equal to x squared minus 1/16. And then x, we can solve for x in the second equation. X is equal to minus 2v, right? So therefore, we can get an equation for u and v. So thus, u is equal to minus 2v squared minus 1/16. So u is equal to 4v squared minus 1/16. So the line y equals -1/4 will constitute a parabola, right? A parabola. But so this is u and then v, right? W plane. So when V is 0, U is -1/16. So it's right here. And so it's going to open that way. Okay. So it's going to be at, so V is ±1/2. That's where it crosses the V axis, right? So yeah, so that would be the image. Okay. So the next thing I want to talk about is so that's how you deal with powers of or singleton functions, right? As that's how you deal with singleton power functions, right? But the next thing I want to talk about is the inverse of the function W equals to Z squared, right? So, and it's mapping, right? So, yeah, so the goal here this time is to find a function F inverse of Z where Z is equal to F of W, right? So suppose that W is, I'm sorry, Z is equal to W squared. And let's say Z is equal to R times e to the I theta, and W is equal to, let's say, rho e to the I phi, right? E to the I phi. Now, this relationship, what this looks like is, in terms of polar coordinates, R times e to the I theta equals to rho squared e to the I times 2 phi, right? So what this means is, 1, R is equal to rho squared, and then 2, theta is equal to 2 times phi, right? But with theta, we have to realize that if we rotate theta 2 pi radians clockwise or counterclockwise, or rotate theta with a multiple of 2 pi, we'll get the same result. So also we can say generally that theta plus 2 pi n equals to 2 times phi, right? So R raised to the 1/2 equals to rho. That's how you figure out what rho is. Okay, and that's part of figuring out the square root of a complex number, right? And then phi, well, this equals to theta plus 2 pi n divided by 2. Okay, let's stop here for a second. Because with inverse functions, the thing that we need to look out for is our function one-to-one on a given set. Okay, so with the polar form of complex numbers, cosine and sine are periodic, right? So what that would mean is we need to look at a branch cut for theta, right? And also, since if we rotate 2 pi radians a multiple number of times, clockwise or counterclockwise, we would get the same result. So what we need to do is look at a branch cut for theta, right? So what that means is we want to look at the principal branch of theta. So So what this means is that theta has to be the principal argument of z, right? And as you recall, the principal cut of the principal argument of z is in between minus pi and then pi. Okay, so therefore, just restrict phi. Phi is equal to theta plus 2 pi, not times n, over 2. Okay. So where theta is basically the principal argument of z. Okay. So this here would be the theta that we would want to figure out this the image, to figure out the image of a set for the square root of z. Okay, so let's look at an example. Example time. Find the image of one half. Okay. So if we're given a the set S as the line where the argument of z is pi over 4, so y equals x in the z plane. So in the z plane, if we're given some line where the argument of z is pi over 4, we want to look at what this image would be under the square root function, z to the 1/2. Okay. So here is my W plane. Okay, so W, U axis and the V axis is there. So what that will constitute right here. So this here is the line y equals x. So essentially a complex number, well, it's just x times 1 plus I, right? It's 1 plus I multiplied by x, essentially, right? So the modulus, right, this will be just root 2 times x, right? And then the principal argument in this case is pi over 4, right? So W equals z to the 1/2. This will be okay, so okay, yeah, so this is R. So so R e to the I theta over 2. So oops, R to the 1/2. So 1/2. This would be your new radius. I'll call it rho. And then phi is essentially the argument of z over 2. Which is pi over 8. So essentially, if this is pi over 4 here, the line where theta is pi over 4, so pi over 8 would be this line that's flattened. So pi over 8. So this is the line where the argument of W is pi over 8. The radius is varied, right? The radius is varied. Okay, we can pick any x we want. And it's going to be just a fixed angle, pi over 8. Okay, so this is the image S prime, right? Under W equals Z to the 1/2. Okay. And then I'll just write out the definition for the principal nth root function. Here's the definition. So if I have an nth root, and in terms of polar coordinates, you just take the nth root of your radius times e to the I of the principal argument of z divided by n. So that's the definition. Okay. And then just the principal argument of z is in between this range, right? Just don't forget that. Here's some problems for you to check for comprehension. Okay. So page 88, 89, 6, 8, 13, 14, 16, 26, 32. All right, so work on those. If you have questions, always shoot me a comment, all right? Send out your comments. For the next time, we'll look at the reciprocal function. So stay tuned. Thanks for watching.